Hi, everyone. Pleasure to be here. Also my first Polar Data Forum, so very exciting. My name is Kim. I'm a PhD student at the School of Computer Science at the University of Sydney. And this work is, of course, with my supervisors, Roman Marchant and Fabio Ramos. And today I will present Frozen Constraints, Fluid Uncertainty, a physics-informed probabilistic machine learning method for the Antarctic ice sheet. So this is concerned with what we've already seen earlier today, a very central data set of polar data in general, ice thickness maps, or equivalently bed topography maps. And there are different purposes that these maps exist for. One of them is ice sheet model initialization specifically, but some other models are more for like general purpose or certain things. But we're focused here on the ice sheet model initialization purpose, and also informed by the purpose, different characteristics of bed or ice thickness could be of interest. And here we're specifically interested in mass conservation for ice sheet model initialization. Also, these models have quite different qualities. So some models are inherently gridded on a fixed grid or mesh, and other representations are rather meshless. And another big question is how easy it is to integrate new ongoing data from every survey into the model. As well as uncertainty quantification, which I will talk more, and also this talk is focused on. Yes, so in general, with polar data, I think I would call it the observational asymmetry in polar data, where we often have a lot of data from satellites on the ice surface, so quite dense data sets there, whereas the subsurface of Antarctica and the Arctic as well, or Greenland, is quite sparse and very different in terms of how much data we actually have available. And this data sparsity still shows in the most up-to-date data sets on ice thickness of Antarctica with, and we saw this earlier by Alice, 93% of the latest bed topography map or ice thickness map, bed map 3, still 93% of the grid cells actually rely on interpolation. So we very much rely on skillful interpolation methods from this data. And also we want some sort of quantification of the model confidence. So if there's huge data gaps, we want the model to kind of represent that we are not that certain what actually is going on there. Also very important, given that there's still big data gaps, is that we want to have data efficient and uncertainty aware strategies of how to survey and how to fill these data gaps and actually have a better understanding of ice thickness. So uncertainty quantification is pretty important, as we can see here. Besides uncertainty for quantification, for the purpose of initializing ice sheet models, mass conservation is another thing that's really important. And a lot of previous research has shown that if there's not mass conservation within the ice flux, then numerical ice sheet models run into problems. So talking about these flux divergences here, so the flux is how much ice mass is actually transported at every point in space. So here we derive it, and I'll talk about that on the next slide, as the product of the ice thickness or height and the velocity vectors. But flux divergences mean that there's sources and sinks. And with ice sheets that are pretty stable over time, we do not expect there to be much of that. So having these in the ice thickness models causes a lot of issues. So mass conservation is an important approach to actually constrain this problem. So there was a lot of great work developing the first mass conservation approaches for ice thickness interpolation. And for example, bed machine, which is very well known by Mathieu Mollingham, applies this to the fast-flowing regions of Antarctica and is a also very widely used ice thickness map for that. And they use in their numerical method, a finite element method, which does have a couple of drawbacks. So it does rely on a fixed mesh and grid. And the integration of new measurements can be quite tricky. It also is computationally quite costly and deterministic, so not a probabilistic model. So my question is, can we use machine learning to address this problem as well? Because it often has computational advantages. It can be probabilistic, and it can also be easier to integrate new measurements as we go. So this is in the field of physics-informed machine learning, which means that we want to integrate physics into our machine learning model in different ways. So there's this framework with basically 3 different approaches. The first one is kind of trivial, that it's called observational bias. So just learning from observations that embody the physics, which only works if we have a lot of observations that do embody the physics. The second one is learning bias, and we refer to them as soft constraint models, where you actually use an additional loss term in the learning of the model that quantifies the physics violation and that therefore promotes to learn more physical solutions. And the third one, which might be the most elegant one, is to actually have an inductive bias that called hard constraint models, where you build the physics directly into the model, could be in the architecture of the neural network or also into the kernel architectures, as we will see. And for this specific problem of mass conservation of ice thickness, we saw the observations are pretty limited, so we can't get very far there. There was a very nice approach of using soft constraint models called physics-informed neural networks by Theisbeck et al. And also some very recent work that is more applied to glaciers, whereas the first one was the Antarctic ice sheet. However, these pins in general have been documented to have some drawbacks too, to not have physical guarantees, and the models are sometimes a bit tricky to train, and also the generalization can be tricky, and having some spectral bias. However, there hasn't actually been a comparison between the different models, and there hasn't yet been any approach of actually hard constraining machine learning models. So that's what we set out to do, and try to also combat some of these drawbacks, but actually compare what can be done. So we very much built on previous assumptions of the previous models, specifically Molecum and also Theisbeck, where we model ice flux vector fields as the product of the sparse ice thickness measurements, which I get from Alice's data set, and then the ice surface velocity here as assuming that it's roughly the same as depth averaged. And we do also do some simplified flow assumptions that so that the continuity equation simplifies to just a divergence-free constraint, where we have negligible thinning and also negligible surface mass balance and basal melt. But for very fast-flowing ice glaciers that have huge ice flux, these are actually super small compared to the flux. So this has been done before as like a realistic assumption. So then mass conservation actually just boils down to implementing this divergence-free constraint that we have here. And this divergence-free constraint can be directly built into the model architecture via a little fluid dynamics trick, where any continuous surface like the one we can see here, if we do take the gradient of it and rotate it, which is then called taking the symplectic gradient, there's a bit of mafia and stuff, then we, by definition, actually yield a divergence-free vector field. So this is a way of always constructing a divergence-free vector field. And this trick is actually used in some machine learning models already that were more sometimes, like in the Hamiltonian Neural Network, targeted at energy conservation rather than mass conservation. But here we have a neural network that takes as input the location, so x and y coordinate, and we predict this value of the stream function at that point in space, then just do this deterministic step of taking this symplectic gradient, which we in machine learning can actually do quite efficiently with automatic differentiation. And then we yield a vector at that point. And the vector field that results is always divergence-free, so mass conserving. However, there hasn't been any applications in glaciology yet, which was quite interesting. So of course, we did that and call it mass conservation on rails. So this has also recently been accepted to a machine learning conference, and there's more details in the paper. I'm not going to go into everything here, but it works very well, and we compared in the paper just to other machine learning approaches to compare these physics-informed machine learning paradigms. Here's just a little glimpse of, in the middle, we're withholding any data to estimate what's happening there and compare it to the sparse real data in the field. yeah, there's more in the paper, but the dfNN actually is more capable at fitting the realistic ice flux vector fields, and achieves better results than the other models, and especially also has the physical guarantees of mass conservation in there. However, I talked a lot about uncertainty quantification. We can't really see that in here yet. And I'm not going to go into all of the detail, but that was a step after this. There's a whole nother pathway working more on Gaussian processes. So some of you might be familiar with kriging a bit more, so it's related to that. But I'm going to not go into all of the detail, but there's certain properties about linear operator theory and also how Gaussian processes are closed under linear transformations. And that can be integrated into the covariance function that basically defines a Gaussian process as well. So this is a probabilistic way of also satisfying this constraint by design. So there are these divergence-free kernels and divergence-free Gaussian processes that have similar properties, but are much more applicable to smooth spatial structures. So again, haven't been applied to our knowledge in glaciology yet. And we do apply them, but even go one step further of combining these two methods and therefore taking on board some of the good properties of either that are very good to model environmental processes. So the dfNNs that we saw first, they're quite good at modeling non-stationarities, more so than Gaussian processes. So for example, when there's a trough right next to a plateau and you have a pretty sharp drop, that's something where Gaussian processes struggle and dfNNs are good. But the dfNGPs, which we just saw the Gaussian process model, they bring the uncertainty quantification and the smooth spatial processes. And we combine them in a Gaussian process framework that through also linear operator principles still can guarantee divergence-free outputs. And just some highlights here. There's more detail to it and more in the papers, and please do talk to me if you're interested. But the great properties we get out of this, so we can take sparse data, and this physical guidance really helps to interpolate also if we only have sparse data and not a ton of data. And we have the divergence-free constraint guarantee of local mass conservation in this combined model. And we also can quantify the spatially varying uncertainty, where here we can, for example, see that over a data gap where there's not a lot of data, the predicted variance is higher. There's much more to it. I'm going to skip some of this here, but we do experiments on simulated and real data from bird glacier and Antarctica and compare mainly machine learning models. So these hard constraint ones by themselves, the combined one, the divergence-free neural Gaussian process, soft constraint models which were previously proposed, and unconstrained models. And overall, the dfNGP with its qualities reaches the overall best reconstruction of unseen flux observations that we withhold. So we just remove some flight lines and try to reconstruct them as if the flights weren't done yet. And quite well calibrated uncertainties as well. So it has good properties with regards to non-stationarities and also multi-scale modeling because of the combined model. I've got the implementation and everything in PyTorch and gPyTorch. It's all reproducible experiments, pre-processing pipelines, and code on my GitHub if you're interested. And yeah, what I just want you to take away is that kind of reiterating the title, Frozen Constraints, Fluid Uncertainty, that hard constraint machine learning with the physics informed in there works really well, especially when data is sparse and noisy, because machine learning models sometimes can be too flexible, and this really helps to guide the learning. And also that they are not only deterministic machine learning models, but also you can hard constrain probabilistic frameworks like the Gaussian process. Yeah, and the resulting product model has some good qualities that are really important to us. And just maybe a tiny teaser, what I'm working on still right now is to use these, this uncertainty quantification to inform survey design. So within the Bayesian optimization framework, you can design acquisition functions to say where you want to survey next to reduce the uncertainty. I've also used a similar model for estimating ice shelf basal melt. So here we model not just the divergence-free, but also the curl-free component. So there's plenty more work that can be done with these types of models, and it works surprisingly well. Trains in like 30 minutes on just one GPU. One more shout out I want to give, especially to the people here that raised their hands earlier, but also to all the data producers. With two colleagues, Julia and Andrew from different institutions, we started machine learning for the cryosphere. So it's this research community where we just want to bring together people that work on machine learning and cryospheric sciences. And I do encourage you to join, for example, our Slack community, for example, to share data sets. But also we share new papers in the space, but it's very open to also people just interested. And we are also going to have a session at EGU again called Machine Learning for the Cryosphere. We had one this year that was quite successful, and we're working on a review paper for this quite big space. There's references if you need them. And please talk to me if you're interested, have questions afterwards, and send me an email.
Amazing, well done. Any questions for Kim? We've got a microphone.
Thanks. It's a great talk.
Thank you.
I am wondering, what if one of your assumptions does not hold, specifically the dH over dt, because we are seeing lots of elevation changes on the glaciers.
Yes. So what I showed briefly towards the end, the project for modeling ice shelf. So there, the assumptions are different, right? So there you would actually model both components, so the divergence-free, but also the curl-free. But there you also subtract from, and that was, I think, a question earlier as well with the thinning data, which we saw in the previous talk too, from either CrySat2 or ISAT2 actually has those thinning rates in there. So you can integrate that as well. However, I haven't tested all of that yet for the ice sheet, but there was more having even stronger guidelines help to at least reproduce the measurements that we withheld, so the unseen measurements, because those effects are so small compared to an order of magnitude, compared to the flux that flows, that actually having higher guidance with this constraint that's placed on it, that actually just help the model to learn much more, rather than saying, okay, there's a tiny component, but we let the model more loose. But it is, there's plenty more work for the future, and this is more like one step towards just a hard constraint machine learning model to implement these constraints, but of course should be tested how well they hold in other areas as well, other than Bird Glacier. Yeah.
Cool, thank you.
Any other questions? Amazing. Okay. Thank you so much, Kim. Round of applause, everyone.